Hello, welcome to the 5.1, 5.3 review. Before we get started, just keep in mind, guys, if you got a lady in your life and you're watching this on Monday, today, then tomorrow is Valentine's Day. So keep that in mind. It's important stuff. Anyway, let's go ahead and get started. So cosine squared x plus sine squared x is 1. Right, we got to know these identities, so always good to go over them. 1 plus tangent squared of x is secant squared x. 1 plus cotangent squared is your cosecant squared x. All right, so those were the first 3 identities that we started with. And here are the ones that we added on a little bit later. So we said that sine of pi over 2 minus x is the same thing as cosine of x. Right? Sometimes you don't see it written with the parentheses, that's fine. Cosine of pi over 2 minus x, that is your sine of x. Right? And we also mentioned that sine is what we call an odd function, which means this negative here can essentially just move out in front of the function. And you're not allowed to do that with everything, right? But only with odd functions, right? So sine is an odd function because it has that property. Whereas cosine, we said, was an even function, right? Which means this negative here essentially just disappears. You can just get rid of these negative signs at will. All right, so we'll be using some of these for these problems in class. We went through about half of each section, so I'm going to go through all of the problems. Hopefully I don't get too long-winded and spend too much time talking. So let's just jump into it. Secant of alpha, right? That's what this letter is, times sine of alpha over tangent of alpha. I would say the strategy here is to express secant and tangent in terms of sines and cosines, right? So we would want to say this is 1 over cosine of alpha times sine of alpha over, and what is this denominator, right? This is going to be sine of alpha over cosine alpha. And you can probably tell, right, these signs essentially cancel. This cosine is sort of going to move up top here. And what we'll have is 1 over cosine alpha times cosine alpha, right? And those two will cancel as well. So the point is this entire expression is equal to 1. The only thing left is that 1 in the numerator. So, interesting. 1 minus sine squared of x over cosecant squared x minus 1. I can think of maybe 2 ways to do this one. One thing might be to swap out the cosecant squared x minus 1 for something, and then we could divide through. All right, so let's think of our identity. Right, we have this one right here. If I were to subtract the 1 on both sides, I get that cotangent squared x equals cosecant squared x minus 1, which is exactly what I have down there, right? So I can swap it out for cotangent. Beautiful, beautiful. All right, so this is the same thing as 1 minus sine squared x. We might swap that out later. We'll see. Cotangent squared x. And yes, it looks like it's probably a good idea to go ahead and this 1 minus sine squared x, right? If you're looking at this identity over here, if you subtract sine squared x on both sides, you'll get that numerator is the same thing as cosine squared x. So we have cosine squared x over cotangent squared x. That is a lot simpler, right? Remember, cotangent is the same thing as cosine over sine. Right, so we could rewrite this way, right? Because we have cotangent squared, and notice these cosines cancel out, which is really nice. And the sine is going to go up to the numerator. So we really, at the end of the day, just have sine squared of x. Nice. All right, let's keep going. Let's go ahead and do this one down here. It's pretty easy, right? So we have an identity right there. That is this one. Right? So we can just turn the denominator into secant squared. Well, what is secant, right? Secant is 1 over cosine squared x. Well, we're dividing by a fraction, so the fraction's just going to flip over, and we get that this is equal to cosine squared x. All right? 1 divided by 1 over cosine squared is going to turn into cosine squared. All right, let's look over here. Now, some of you guys might know an identity already for this. We haven't really officially gone over it. So what I would expect you guys to do is to recognize here that cotangent is the same thing as cosine of pi over 2 minus x divided by sine of pi over 2 minus x. Right, and the pi over 2 minus x part stays there because, we know that cotangent is cosine over sine, so the input is going to be the same whether you have it written like this or if you, have it written broken up into cosines and sines. So just keep that in mind. Right, we're not just going to have cosine of x over sine of x. Right, the inputs have to be the same. And from here, we notice that cosine of pi over 2 minus x, that's an identity, right? That turns into sine of x. The bottom, sine of pi over 2 minus x, turns into your cosine of x. We have times cosine of x. Well, those cosines are going to cancel. So we have a nice sine of x down here. Okay, let's keep going here. We have a lot of problems to get through. See, I think I did this problem for some of the sections, but not all of them, right? So I think the way I explained it was you probably want to deal with this negative here first, right? We don't really have any identities that have a negative x inside of them, so we want to move that negative or get rid of it somehow. So I would first rewrite it this way, just so it's very clear what comes first. Do we square it first and then pull out the negative, or do we pull out the negative and then square it? Right. This way it's crystal clear what you're supposed to do. Right. This expression and this are mathematically the same. Right. One is just a shorthand way of writing the other. And so now we can see, okay, let me go ahead and start inside of those parentheses and pull the negative out. So we'll have negative sine of x squared. Beautiful. And now, negative sine of x times negative sine of x, that's going to be plus sine squared x. Wonderful. All right, and this is cosine squared x. And from here, you could go two different ways, and maybe I'll show both of them. Right. So what you could do is you could substitute in for sine squared and turn this into 1 plus 1 minus cosine squared x over cosine squared x. And this whole thing would simplify really nicely. So you would have 2 secant squared x and then minus 1. So that's one option. That's a valid answer. And maybe in a different color, what you might want to do is just divide through by cosine. So I'll do that in green. And that's going to give you, it looks like, secant squared x plus tangent squared x. Right? And that's also pretty simplified. It's really just a matter of preference, which one you would put as your final answer, but they're both pretty much as far as you can go. Notice how we don't have any fractions in this one or in that one. Right, so that's sort of the goal. You want to get rid of all the fractions. You don't want to have any negatives inside of a square root like that one. So anyway, those are two valid answers there. Here we have sine of x plus cosine of x all squared. Right, so the first thing you would probably want to do is go ahead and distribute this out. So first I'm going to rewrite it so that I can see everything that's supposed to multiply, right? That's what that squared means. So now I'm going to do my distribution. So I end up with sine squared x plus sine of x cosine of x plus, well, this is going to be another sine of x cosine of x plus cosine squared x. Cool. And these two terms at the very ends here, right? Those added together, because we can add these in any order we want, right? Sine squared plus cosine squared, that's 1. And then if we combine these two, right, these are like terms. So, and there's 2 of them being added together. So we have plus 2 sine of x cosine of x. And that is all we can really do. We really can't go any further than that on this problem. Okay. Feel free to pause the video at any point and sort of go back over the explanation. I just have to move quickly so that this video isn't an hour long. So the strategy for this one, you notice these parentheses are kind of suggesting to you that distribution is going to help. Right? If you have 2 things that are sort of multiplied in parentheses, you probably want to distribute. That's almost always going to help you. So let's go ahead and try that out. Let's see what we get. Well, 3 times 3 is 9. 3 times 3 sine is 9 sine of x. Negative 3 sine of x times 3 is minus 3 sine of x. And then minus 3 sine of x times positive 3 sine of x is minus 9 sine squared x. And notice those 2 middle terms here cancel out, which is really nice. All right, so we're left with 9 minus 9 sine squared x. And you guys might want to already use the identity at this point, but I would highly recommend pulling the 9 out first so that you know exactly what you're dealing with. Right, so I just undistributed the 9, or I pulled it out, I factored it out. And now I can see 1 minus sine squared, I know what that is, right? That's cosine squared x. If you try to use the identity prematurely, you could make a mistake there. So I just wanted to pull the 9 out first. And lastly, for this section, we have cosine of x times cotangent of x plus sine of x. Right, so the recommendation here is if you have a cotangent or a tangent, it's very likely you're going to have to break that up, right, into cosines and sines. So this turns into cosine of x over sine of x. And everything else stays the same, of course. Well, let's go ahead and multiply this whole factor out and see what we have. All right, we have cosine squared x over sine of x. Well, that's interesting. Well, we have a cosine squared. If I get this one over a denominator of sine, that's going to turn into sine squared over sine. And that's probably going to use an identity here, right? If you get it over the same denominator, that's what you get. Okay, well, cosine squared plus sine squared, that's 1. So this whole thing turns into 1 over sine of x, which is the same thing as cosecant. Just as a side note, if you didn't quite follow this part right here, right, I multiplied by sine of x over sine of x, right? That's what I did. I didn't write down that step. All right, so that's 5.1. So the goal is you want to simplify it as far as you can go. Remember, sometimes there's multiple right answers, and I'll account for that on the quiz. But in general, your answers should not have any fractions, right? Notice how none of my answers have any fractions whatsoever. You just essentially, you're only going to have maybe 1, maybe 2 terms by the end of it, and no fractions. And also no negatives inside of a parentheses like this problem over here. So anyway, just want to point those out. That's your goal, right? All right, so let's move on to verifying. This first one I may get back to at the end, but I don't remember where the equality is supposed to be. Maybe this plus sign was meant to be an equality. I don't quite know. So I'll have to get back to it maybe at the end here. So I'll skip it for now. All right, let's start with this one. So secant squared of pi over 2 minus x. Well, what is secant? Right, that's going to be 1 over cosine squared of pi over 2 minus x. All right, minus 1. Oh, and by the way, the reason why I'm starting with this left side, I should have clarified that, is because I can see there's a lot more opportunities for substitution, right? Namely, like this thing, I know I'm going to have to use an identity for that. I also know what secant is, right? It's 1 over cosine. And because of the fact that I have this fraction here, I know it's probably going to help me to combine it with this term over here. So there's just a lot of little hints that the left side is a lot easier to work with here. So now let me use the substitution for this guy, right? We know that cosine of pi over 2 minus x is sine, right? So this is 1 over sine squared of x minus 1. Okay, so we are almost done here. Now let's try to get this 1 over a common denominator of sine squared. Well, that's not too bad, right? This will turn into 1 over sine squared x minus sine squared x over sine squared x. Right, it's the same thing as 1. And notice what we have, right? This 1 minus sine squared in the numerator is going to turn into a cosine squared. So let me continue the work over here, right? We're going to get cosine squared x over sine squared x is maybe equal to cotangent squared. Well, that's exactly what it is, right? So as a final step, let's go ahead and write it. Cotangent squared x equals cotangent squared x. So yeah, just notice the left side was a little easier on that one. Like if I were to start on the right side, I really wouldn't know what to do with that other than maybe turn it into cosine squared over sine squared. But, you know, other than doing that, I really wouldn't know where to go from there. It's just not as simple to see or straightforward to see. So anyway, let's jump over here now. Again, we probably want to start with the left side here, right? Notice I know a substitution that's going to deal with this negative. I also have these parentheses that probably means distributing is going to help me out here. Whereas the right side, I really don't know what to do with that cosine squared. I mean, maybe I could substitute it out, but what would I do from there, right? There's just more stuff on the left side. So it's better to deal with that. As a first step, I would deal with this negative sign first, right? We know the odd identity for that. Right? We can pull that out of the sine function. So this will turn into 1 minus sine of y. No, let me just keep consistent here. No parentheses. All right, so now let me distribute this out. Okay, so we get 1 minus sine of y plus sine of y, and then minus sine squared y. Right, those are my 4 terms. Well, notice the 2 middle terms cancel, and we're left with 1 minus sine squared y. Oh, but that's exactly what cosine squared is. Right, so cosine squared y is equal to itself. Boom. Yeah, that one's not too bad. There's a lot of hints at what you're supposed to do. Let's look at this guy over here. Again, left side has a lot more going on there. So I would work with the left side. And what I would probably start with is this tangent and cotangent. Always a good idea to turn those into sines and cosines. right? So I know that tangent is sine of x over cosine of x. I know that cotangent is cosine of x over sine of x, and this is all on top of cosine of x. Well, look at that. Right, this cosine will cancel with this one. This sine cancels with this one. So we're just left with a big old 1 in the numerator. All right, I mean, it's like if you had 3/4 times 4/3. What do you get? You get 1. Right, same kind of principle here. And 1 over cosine, we know that that's what secant is, right? So the left side just turns into secant of x. Yeah, that one really wasn't too bad. Again, if you started with the right side, how in the world would you know to turn this 1 into the multiplication of tangent and cotangent, right? It's just not as intuitive. So yeah, start with that left side. It's got more stuff. All right, so let's look at this one over here. Now this one, I may or may not have covered it in class with you, but there's one side that's better than the other to work with here. You may think it's the right side, some multiplication. That may or may not work. In fact, for all of these verification problems, you can actually prove them with either side. Just one is usually easier. I would say that the left side is easier in this case. It's not. I know that a lot of these problems, you've used the left side here, but just know that it could very well be the right side, right? But really the thing that intrigues me here is that minus sign, right? So the reason why that kind of draws me in is that I know that this thing over here is going to turn into a fraction. And if I turn it into a fraction and then I combine it with this term, with the cosine, by getting a common denominator, it's probably going to simplify and just turn into the right side. So I kind of already know a couple steps ahead what I'm supposed to do, whereas the right side, I don't really know what to do with that. So secant is 1 over cosine of x. And you know what? While we're at it, right, let's convert the cosine of x into something with the same denominator, right? So cosine squared x over cosine of x. Okay, well, this is 1 minus cosine of x, cosine squared x over cosine of x. Forgot to write these little equals question mark things. Well, 1 minus cosine squared, that's an identity, right? That turns into sine squared x over cosine of x. And from this point, I think it would probably be best to split up, right? Notice how we have a sign in front over here. So we probably want to go ahead and split up that sine squared. Let's pull 1 out in the front. And then let's leave 1 up top in the numerator. And look at what we got, right? We have the sine of x in front, and then sine over cosine, that's the tangent. Beautiful, beautiful. And then we have this thing over here. And I think maybe one of the sections I taught through this review, we went through, I think it was 3 different ways to do this problem. So I want to go through those 3 different ways. There's a lot of ways you can prove this. Let's see. Way number 1 would be to actually start with the right side and say, okay, 1 minus 2 sine squared beta. Right, that's what this symbol is. It's called beta. It's a Greek letter. Greek alphabet is alpha, beta, gamma, delta. Beta is kind of like B. But anyway, we want to start with the right side, and what we could do is we could turn 1 minus 2 sine squared into 1 minus sine squared beta, and then minus another sine squared beta, because that's what that coefficient of 2 is. It's telling you how many times you're subtracting it away. And if we notice, right, this part right here is an identity. Right? And what is it? Well, it's just cosine squared beta, right? And so we end up jumping to the answer really quick with only maybe 2 steps of work. So that's really nice. Really nice, really nice. Okay. How else could we prove this? Well, we could also start with the left side. So I'll do that in a different color. Let's do red. We could start with the left side and make a substitution for cosine squared of beta. It's a weird substitution, but it's actually going to work. If I replace that with 1 minus sine squared beta, right? I'm just working with the left side here. Well, look at what we get. Those 2 sines combine together, and we end up with 1 minus 2 sine squared beta. Bingo. Want to see a third one? Let's do it. What if we substituted for the one thing you would never expect? What if we substituted for this 1? We could do that. You can definitely do that. We have an identity all the way at the top that tells us what 1 is equal to. All right, let's use it. Let's use it and just see what happens. All right, let's experiment here. Well, if I replace the 1 with cosine squared of, oh, sorry, we're not using x, we're using beta. Beta plus sine squared beta. And I have this minus 2 sine squared beta. Think of the sine squared beta as like an x, right? If you have plus 1x, right, there's a coefficient of 1 there, and then minus 2, well, that's going to end up turning into minus 1, right? And so this whole thing turns into cosine squared beta minus sine squared beta. Boom. So I'm just trying to show you just how many ways some of these problems can be done. This one can be done in at least 3 ways. There's probably a 4th way that I'm not even thinking about. But they're probably going to be more complicated than these 3 ways. These are the 3 fastest ways I know. All right, so let's move on to 5.3. And here we have 6 problems here. I think I did 2 of them in class, maybe 3, depending on which class you were in. So I'll just go through them one by one. Remember, because we're on the interval of 0 to 2 pi, that means our solutions have to be between 0 and 2 pi. So we're not going to be doing plus. We don't have to add that plus 2 pi n stuff that I showed in class the first time I taught you all this. But as a first step, right, you want to go ahead and isolate whatever the trig function is. So we get 4 cosine squared of x equals 1. Right, divide both sides by 4. We get cosine squared x equals 1/4. All right, take the square root, and remember, right, if you take the square root, you're going to have a plus minus here. Right. And what is that going to turn into? It's just going to turn into plus or minus 1/2. Right? Square root of 1 is 1. Square root of 4 is 4. Square root of 4 is 2. So cosine of x at the end of the day has to be equal to plus or minus 1/2. And from here, this is where we want to get a sense for, okay, where does that happen on the unit circle? What places? Well, I can think of at least one place, right? So this angle line here, this is pi over 3. Right? This is where cosine equals 1/2, right? Because the coordinates here are 1/2 radical 3 over 2. So cosine is equal to 1/2 there. In fact, just by symmetry, I know that whatever this angle is, right below it, if you just fold it down, that should also give me a cosine of 1/2, right? It's going to have coordinates of, not negative 1/2, positive 1/2, negative root 3 over 2. So that's another one. Well, what is that angle? That's 5 pi over 3. Okay. What about negative 1/2? Where does that happen? Well, that's going to happen if we take these triangles and fold them over the y-axis, right? We get something like this. We get a point out here, and we get a point out here. This is where the 1/2 part is negative. We get negative 1/2 root 3 over 2. And over here we get negative 1/2 negative root 3 over 2. We don't care about the root 3 over 2 because that's sine, right? Not cosine. So the point is, these are the only 4 spots on my entire unit circle where cosine is equal to positive 1/2 or negative 1/2. And these other 2 angles, right? This is going to be 2 pi over 3. And this one down here is 4 pi over 3. So just make sure you know your unit circle, right? You have to know, where the angles are and kind of more or less what they look like, because these are our solutions. These are the solutions. So what does this tell me? Well, this tells me x equals pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Right? Those are the 4 solutions here. Most of the time, remember, you're only going to have 2. The only reason we got 2 more was because of that squared part right there. Gave us a plus and a minus. Okay, so let's move on to this one over here. This one's really not too bad. So again, solve as far as you can. So subtract 1. We end up with 2 sine of x equals negative 1. Well, if you divide by 2, that tells you sine of x equals negative 1/2. Right, so the question is, where does that happen? Okay, let's draw another unit circle. Boom, boom. Well, remember, sine is the y-coordinate, right? And the only places I can think of where y is 1/2 would be kind of around here on the unit circle and around here. Right? The coordinates here are radical 3 over 2, negative 1/2. And then over here, the coordinates are negative radical 3 over 2, negative 1/2. Well, what are those angles? So this one is 7 pi over 6. This is your 11 pi over 6. So those are my 2 solutions. Right? So x equals 7 pi over 6, 11 pi over 6. Cool. Only 2 solutions there. Also keep in mind as well, right? You guys will have a calculator. You will. And so an alternative way to do this, granted, it's not going to give you those pi's, right? But it is going to give you the right numerical value. You could graph this left side right here in your TI calculator, right? Just say y1 equals this stuff on the left here. And then you could also look for the zeros, right? So where does that graph touch my x-axis in any way? Does it, whether it passes through it or whether it just touches it and bounces off, those are going to be solutions to this equation. The only problem is, instead of giving you 7 pi over 6, they might give you something like, maybe that first solution might be, let's see, I wish I had a calculator here. It could be something like 3.6 something, right? It's going to give you a decimal. You're not really going to know where the pi is. Now, this is the way your answers should be written. You should have the angle in radians with pi there. But that would be at least one way to see if you're on the right track. Like if you thought maybe that this was the right answer, but you're shaky on your radians, what you could do is you could put that, put it into the calculator and have the calculator spit out the decimal value and then see if it's the same thing as the one you see on the graph. So that's just another way you could do it. All right, let's try this one over here. This one's kind of funky because we have sort of the multiplication of two things equal to 0. Well, if you think about it, the only way that this left side could be equal to 0 is if either this sine of x is equal to 0, or if this part is equal to 0. So if we find the specific places where either of those parts are equal to 0, that is a solution for the whole thing. So let's consider the first equation, right? Sine of x is equal to 0. Where does that happen? Well, again, draw a little circle for yourself. Where does sine of x equal 0? Well, I could only think of two places, right? At 0 or at pi, right? We're always working with radians here. 0 or pi, because the y-coordinate is 0. So that gives me two solutions. All right, let's look at this other one. All right, so what if sine of x sine of x plus 1 is equal to 0? Well, we would want to subtract the 1. We get that sine of x equals -1. And we do the same process, right? Where does sine of x equal -1? Well, there's only one spot, right? It's down here. That's where the y-coordinate is -1. And that angle is 3 pi over 2. So all three of these red angles are solutions to the whole equation, right? So my answers here are x equals 0, pi, and 3 pi over 2, right? You want to list all solutions, not just one, not just two, all of them. All right. Let's try this one over here, right? Radical 3 cosecant of x minus 2. I think I did this one in class for most sections, but let's go over it again. So again, try to solve as far as you can go. So we're left with this. It's equal to 2. Divide both sides by root 3. So we get cosecant of x is equal to 2 over root 3. And also notice, right, cosecant is 1 over sine of x. Well, if I take the reciprocal of both sides, that gives me a really simple equation. Sine of x equals radical 3 over 2. All right, so that's as far as we can go. Now let's draw a little unit circle on the side here. Where does the y-coordinate equal radical 3 over 2? Well, there's only two places. There's sort of this angle line over here, and there's this angle line over here. So the coordinates here are 1/2 radical 3 over 2, and we have -1/2 root 3 over 2. Those are the only two spots. And so what are those angles? Well, this is your pi over 3, and this over here is 2 pi over 3. So our answers are just those two, right? X equals pi over 3, 2 pi over 3. And that's it. So even if it looks a little weird at the beginning, right, just solve as far as you can. You want to get it to sine or cosine equals something. All right, now let's try this one over here. So again, solve as far as you can, right? Divide both sides by 2. So we have cosine of x over 2 equals radical 2 over 2. Now at this point, we cannot do anything about this over 2 business inside of the parentheses. We don't really have a way of dealing with that or making it go away. So we actually have to kind of solve it as it is right now. And what you want to do is you want to think about it in a very careful way, right? So first off, what we're going to do is we're going to find the angles where cosine usually spits out radical 2 over 2. There's only two places, right? There's this one. We're dealing with cosine, right? The x-coordinate, right? This is radical 2 over 2, comma, radical 2 over 2. And the other place is going to be right below here. All right, so this is, why did that happen? Radical 2 over 2, radical 2 over 2. Oh, sorry, the y-coordinate is negative there. But the point is, those are my two angles. So this one over here is pi over 4. This one over here is 7 pi over 4. All right, are those my answers? No. No, they are not. All right. So where we go from here is that we want to set x over 2 equal to those two angles and solve for x. So what we would say is x over 2 equals pi over 4 and 7 pi over 4. Well, you might be wondering, okay, why are we doing that? Well, remember, these angles make cosine spit out radical 2 over 2 if the entire input of cosine is equal to this angle or this angle. Right? But the input of cosine here is an expression that has more stuff to it. So we actually have to whittle it down now that we have this equality and solve specifically for what x should be. Right? So what we would want to do is we'd want to multiply both sides by 2. Let me just sort of put parentheses here. This is not a point, by the way. I'm just trying to list what we're doing here. Right? So the 2's cancel, and I get that x equals, right? It kind of distributes here, right? You want to multiply both those angles by 2. So it turns into 2 pi over 4, which is the same thing as pi over 2. And then 7 pi over 4 turns into 14 pi over 4, which is 7 pi over 2. And these are the solutions to the equation. And if you don't believe me, right, just check it out yourself. Check it out yourself. So if I were to take these solutions and plug them back in, right? Let's say I do pi over 2, right? So I'm going to put pi over 2 here. Over 2, what does that turn into? Well, pi over 2 divided by 2 turns into pi over 4. Oh, and look at that. We know what cosine of pi over 4 is. It's radical 2 over 2, right? And so that's why that's a solution. So these solutions are accounting for that x over 2 part. You have to account for that. You cannot just get rid of the 2 just because you don't like it being there. So anyway, let's move on to this one. We're also going to see something similar here. So tangent of 3x equals 1. Okay, well, we're kind of at the simplest part of this equation already. But tangent is very hard to visualize. So let's think about this, right? We know that tangent of 3x is equal to sine of 3x over cosine of 3x. And remember, that's basically like the y-coordinate on the circle divided by the x-coordinate. So let's just think about all the angles we know. And when does the y-coordinate of that angle divided by the x equal positive 1? So let me draw some axes here. And to start with, I want to just start with this first quadrant. So I'm going to put a line out there, out here. And let's just consider that first quadrant. This point over here is 1, 0. This one is radical 3 over 2, comma 1/2. Should probably make the thickness smaller here. This is going to be your radical 2 over 2, radical 2 over 2. This is your 1/2, radical 3 over 2. and this is your 0, 1. And so what is the tangent at each of these angles? Well, this one's pretty easy, right? It's 0 over 1. Well, that's 0. That's not what we want, right? We want 1. We want tangent to spit out 1. What about this one? This is 1/2 divided by root 3 over 2. Well, that's not equal to 1 either. All right, let's move on. This one is going to be radical 2 over 2 divided by radical 2 over 2. That is equal to 1. So we found a pretty critical angle here, right? This is pi over 4, right? Let's just check some of the others, just to be safe. Right? So this is radical 3 over 2. Let me write the slash a little sideways there. Divided by 1/2. Okay, that's not equal to 1 either. And then this guy over here is 1 divided by 0. That's undefined, right? So obviously that doesn't work. So it looks like our solutions are going to probably show up on these pi's over 4 sort of angle lines. Right? So what you might want to do from there is check the others that have the same denominator and see what they give you. Well, if we look over here, right, this is 3 pi over 4. Does that give you a tangent of 1? Well, the coordinates here are negative root 2 over 2, comma, root 2 over 2. Well, that's going to give you a tangent of negative 1, right? So that doesn't work. If we look at this one over here, right, so this is 5 pi over 4. Well, the coordinates are negative radical 2 over 2, negative radical 2 over 2. All right, well, if we take the y divided by the x, you get 1, right? So that's the other solution. So it looks like, well, and these are not final solutions, right? These are the angles that are involved in the solutions. But remember, because we have this 3x, we need to account for that. So this is where we, just like we did over in this problem, you need to set the input of tangent, which is the 3x, equal to those two critical angles, right? Pi over 4 and 3 pi over 4. And now to get rid of the 3, right, you have to divide both sides by the 3. Well, what do you get? You get that x equals pi over 12, comma, and 3 pi over 4 divided by 3 is just going to turn into pi over 4. Right? And so these are the solutions to the equation. That one took a lot of thinking. Right? And part of the problem is tangent is very, very hard to visualize. Right? It's not just the y-coordinate, it's not just the x, it's the division of those two things. And so you can't really visualize it on a unit circle. You just have to play around with the coordinates and divide the y by the x and see what you get. So for that reason, this one took a little bit longer because we had to actually check multiple angles and see what the tangent at that angle was. But the point is, this is the entire review. Hopefully this is not over 40 minutes. I'll go ahead and stop it here. And, just keep in mind for the quiz, the first section will just be basic trivia on these identities, right? You'll basically just be filling in a blank, right? If I put cosine of pi over 2 minus x equals, I'll put a blank here, and you'll literally just write in sine of x, right? So that's 5 pretty easy points on the quiz. And then you'll have sorted problems from this section, this one as well, verifying, and then solving equations, right? So should be a really standard 25-point quiz. So anyway, I don't want to waste any more of your time. So thank you for watching, and good luck studying. And remember, Valentine's Day is tomorrow. So if you have a special lady, right, do something special for her, and have a good day.